This is going to be an introduction to the programming language I've been working on. I'm not going to go into detail for like many things because otherwise I'm going to run out of time. So this is the repo. Essentially, my language I've been using right now for a while, trying to get familiar with everything and really enjoying is C++. And over the past maybe like 3 years, I learned about like modern C++ and C++ 17, 20, 23 features. And I've also experienced some of the pains that you get when you're writing C++ and it doesn't work and the compiler isn't really helping you. And so I was thinking, you know what? I bet I could do a programming language and have it like fit. I want a language that's a better fit for how I use C++, essentially. So essentially, my idea for the language is all the features of modern C++ that I use, I want to have them as language elements instead of standard library elements like C++ standard library elements. So I'm now going to show you the structure of the project. Essentially, if you open the repo in like Visual Studio and you import, there's 4 projects. There's one which is just the Google test project. I was trying to implement CI/CD. I couldn't manage to call the test properly and I stopped. So you can completely ignore that. So that's the Google test project. The other projects are run, which is what you'd call to compile from the command line. I basically never use it. I just call like, this would just call like transpile this thing here with the files from the folder that you pass in. Test is similar. You just pass one argument. This is main here. You pass one argument and it calls test transpile all folders from that. There's different tests. There's one for like reading the files. Can you parse all the code? The intermediate representation that you produce from the code, testing if that's correct. Template selection. Template selection is kind of like its own little thing, so the tests are very much separate. And then transpilation, like actual integration. So the arg that I pass right now, you can see it here, properties, debugging, test. This is that folder here, test. And so for each folder in the test, it looks for a test.caesium file and either expected error or expected CPP. So basically like the code that's supposed to be produced or the error that's supposed to be produced. And the test passed if it produces the right thing. It's that simple. Basically, there's another thing that you can do to test is to run the generated code. So here I have a project that I made, Caesium test transpiled, and I just added the additional include. I include tests, and then here I include 0 expected dot CPP. And it's this file here. So you can see that it's the expected. So it's not perfect. I guess it could be the produced, but the thing is that the produced is not produced if it matches the expected. But the expected is always there. Now it can be a little bit misleading because I can run this and it runs and it outputs true. But the thing is that that's not the actual code that was produced by the transpiler. There was no code produced. It produced an error because I was messing with this code earlier and I am trying to implement 2 things at once. And so this is not going to work right now. But I can still test that the expected code makes sense, which is probably more important than checking if the generated code makes sense, because the expected code is always supposed to make sense, while the test can fail. So anyway, and then the last part of this is the actual core project, which contains the logic, I want to say. So these things are just like one file, right? Like main and main. But this thing has, the biggest thing here is core. So if I start from the beginning, there's like primitives. So those are like the tools I use to build the grammar. And then the other thing is the tokens. So with these 2 things together, I can build the grammar. And then, so the tokens are like keywords and symbols, really. And there's also stuff like a you can see word. Where is it? So word, floating point number, integer, or string. So those are not like those are like variable, but all of the other ones are like static things. And then from that you can build the grammar. So I really like how I did the grammar. Basically it's all types, right? So for example, parent argument is a type, and it's just a type alias actually. It's just and, parent open, function, comma star, function argument, parent close. And once you have the grammar, what you can do is there's a little bit of a mismatch between how you parse things and how you want to access them. So for example, let's look at parent arguments. It's not maybe the best example, but it's decent. So if I look through here, you can see there's a struct parent arguments, and you can see here, all it is a vector of function arguments. So the difference between this parent arguments and that parent argument is that you can take this, completely ignore the parent open, the parent close, and the commas, and just get the function arguments, and then from that you build this, right? So this is what you want. This is like the content. And this is like how you're supposed to parse this. So you're kind of getting rid of the detail and putting it in a way that is easier to deal with. Sometimes it's even worse because some rules use like some types of recursion and stuff, and I can get rid of the recursion in the structurized version. For example, like expressions and stuff. Now, once you have the representation that you need to parse and the representation that you want, there's a file here, the structurizer. It tells you how you go from one to the other, essentially. So I have like get struct. Most of these things are called get struct, and they take the grammar rule and produce the node struct representation. So as you can imagine, the implementation for converting a grammar rule to a node struct equivalent is quite simple for most rules. For example, for parent arguments, it's extremely simple because we just need to get the comma star. We do we do dot get comma star. So on an and, dot get is the and is essentially, it uses a standard tuple underlying representation, so you just do standard get with that. And then we do dot get view on the comma star. The comma star is a type of knode, and get view returns the nodes. So that's the vector. And now that we have the vector, we just transform it, we map over them, and we call get struct on each argument. Now there's probably, you can see here, function argument, right? So this is the get struct for the function argument. It returns a node structs function argument. And it's a little bit more complicated, but same deal. We're just looking at the stuff from the grammar rule and transferring it into the structurized version. And yeah, then we create a vector of that, and that's our parent arguments. It's just a vector of the function arguments. Extremely simple. So when you think about it, the entire code of the parser is to create the final representation I'm dealing with. First, you have the code that you tokenize. So you get a vector of tokens. So essentially like symbols and stuff like words and ints, right? And keywords, of course. And then after that, there's the primitives. You build all of them, and all of the build functions are here. It's not even 200 lines of code, I think. Yeah. So line 200 to 370. Yeah, like that is nothing. So this is all the code, and then you have the structurizer, which is quite a bit of lines to be fair, but it's not even 1,000 lines. And some of this could be probably simplified, you know? Like, I didn't try to save space or anything here. There's Why is there there's a huge block of code that's just commented here. I feel like that is not okay. Let's remove that. Anyway, so yeah, it's only like a bit over 1,000 lines to produce the final representation that I'm actually handling. And that's a representation that if you look through here, maybe a bit lower, when I'm dealing with functions, that's the thing I'm dealing with, node structs function. And same with like node structs reference and mutable references, function argument. That's the final thing that I use. And then I implement my logic on top of that to produce C++ code. So I hope you enjoyed this overview of the first phase of compilation, which is just setting up all the data before you actually produce anything. And in the next video, I think I'm going to go over the transpilation process and maybe a few visitors, like transpile expression, for example, type of type names, what are the difference between the types and the type names, and some of the other types that I use to manage the transpilation process, such as the type information, non-type information, variables, and the state. I think that will be probably a longer video than this, but maybe more interesting, but it wouldn't really make sense without the first part, so that's going to be coming out very soon.